Okay, today we're happy to have Shruti Paranjape all the way from Davis, California to tell us about the double copy.
Cool, so I'm happy to talk about stuff I've been thinking about recently. As John said, I basically climbed up one flight of stairs but to be here. But I do hope that there's still stuff that I can tell you that you find interesting. In case this is too elementary a level, please feel free to ask questions which ask for more details, or if something is not elementary enough, feel free to ask questions. So the talk will mostly be based on this paper that I just put on the archive with Yaroslav, two of his students, Tara and Umut, and Carol Camp, who is faculty at Charles University in Prague. Okay. Cool. So the playground for the talk will be spontaneous symmetry breaking. So this spontaneous symmetry breaking happens when the Lagrangian that describes your theory has a certain symmetry, but if you're looking for vacuum states of that Lagrangian, then they don't have that symmetry. So the ground state breaks some symmetry, and this shows up in all kinds of situations in physics. A wide variety of phenomena can be traced back to spontaneous symmetry breaking. Okay. Now, from the point of view of the spectrum of the quantum field theory, when you do have spontaneous symmetry breaking, Goldstone's theorem tells you that there will exist a massless state in your spectrum, and the symmetry that is broken will be non-linearly realized on that massless state. Okay, so this is a toy picture. It's telling you that this rotational symmetry is spontaneously broken by whatever ground state you choose, which will sit on this circle over here, and the symmetry will act non-linearly in that it will move you from this ground state to this ground state all around the circle. So this is of course a specific example. You can consider a general thing where you start with some symmetry group G and you break it to some subgroup H, and that leaves a bunch of broken currents that live in this coset G mod H. Now at slogan level, meaning that there are some exceptions to this rule, the number of Goldstone modes, the number of massless states, are equal to the dimension of the coset G mod H. So that gives you the number of Goldstones. And one way to see this is because the broken currents live in G mod H, and the broken currents, when acting on the vacuum, produce these massless states. Okay. Now, the kind of symmetry breaking scheme that we will be looking at today is SUN cross SUN breaking to SUN. Which means that the coset G mod H is just SUN. Now you can open Weinberg volume 2, and he'll tell you exactly how to write down a Lagrangian that is compatible with this symmetry, both linearly and non-linearly realized symmetry. And you can write it in terms of U, and we will favor actually writing it in terms of these pi's or pions, simply because then we can say that, okay, these are just some set of scalar fields with some flavor index A. Okay. So famously, at leading order, such a Lagrangian is a nonlinear sigma model that has this structure over here. So it's a two-derivative theory at leading order. Yeah.
Should a GAB be canonical delta or less the metric?
So this GAB is some. It's a function of pi. So it has some pi dependence. And yeah, you're right. So when I expand it in small pi, it will be like 1 plus, or delta AB plus. Yeah. So the kinetic term, which is just two derivatives and two fields, will just look like this. But when I write this down, I also include higher order in pi terms, which will be interaction terms.
So is there an obstruction to going higher order in derivatives, or you just haven't got that far yet?
So this is the universal part, and then we will add high derivative corrections that are compatible with these symmetries. Yeah. So, yeah, there's no obstruction to doing it. Good. Well, okay. So it's because we're thinking of all of this as some effective field theory, and so there's some mass scale and high derivative corrections are then suppressed by that mass scale. Okay. So the reason I call them pions is because well, in QCD, these would be pions. They would be approximately massless, not massless, and would come from up-down chiral symmetry. Approximate up-down chiral symmetry. Okay. Now, one very nice property of scattering amplitudes of pions is that they contain what is called a Adler zero. So that means that if I take the momentum of one of the pions to 0, then the whole amplitude vanishes. So it has a 0 at some point. Now, this property, along with various others of nonlinear sigma models, can actually be fully understood on shell. So you don't have to write down a Lagrangian. So the off-shell properties I just talked about just now was that the vacuum is symmetric, that the broken symmetry is nonlinearly realized, and that the Lagrangian is fixed at 2 derivative order. Right? But if instead you look at what's happening on shell, all of these properties have some analog on shell. So if you wrote down the Watt identity of the broken current, you could use that to understand the fact that there is this Adler zero over here, and the fact that the Lagrangian is fixed comes down to some on-shell recursion relations for the scattering amplitudes. Okay. Good. So just before we go forward, I'd just like to point out that this only happens when the coset is a symmetric space, because otherwise your amplitude actually won't vanish, or doesn't necessarily vanish in the soft limit of the pion momentum. But we don't have to worry about this. We're going to only talk about SU and nonlinear sigma models.
So, but it doesn't, I mean, from this outline, I don't see where the Adler zero appears here. I mean, except that it comes out at the end. Is it somehow an input, or what do you mean when you say, I mean, in principle, why couldn't you do this, for example, this on-shell game in a non-symmetric coset? What would go wrong?
So you could write this down.
Right.
And you could...
Oh, there it is. I'm sorry. Yeah. So that's...
So the minute you try and use this Watt identity to conclude that the soft behavior is given like this, the soft limit vanishes, there'll be an obstruction to that that soft limit, so it won't vanish. Instead, you'll get some contribution that depends on 3-point amplitudes. Yeah.
So you're saying it's not known how to do it on shell? Because off shell, we can certainly do the Callan-Coleman-Rassimino thing, right? For a non-symmetric coset, we can certainly do the CCWZ thing.
Yeah.
But you're saying we don't know how to do the on-shell version?
That you can, it's just not as nice. I mean, you need to have some kind of guess for, basically, when you take the soft limit, you're going to get something that doesn't vanish. You need to have a guess for what that thing is. And if you have such a guess, you can still write down an on-shell recursion relation. It's just not as neat, and it's harder to figure out what properties all amplitudes in that theory will have. Yeah.
Okay.
Yeah. When I show you the recursion relation, I can point out what goes wrong. Yeah. Okay. Good. So another nice property of nonlinear sigma models is what is known as color-kinematics duality. So this was first pointed out by Born, Carrasco, and Johansson, who I will frequently refer to as BCJ. And so the property is as follows. So if you look at a nonlinear sigma model amplitude, the NLSM amplitude can schematically be written in this way, where at tree level, where it has a bunch of propagators in the denominator, there's some color information, so this would be some product of structure constants or trace over generators or something like that. And then you have some kinematic information that I've called N. Okay. This is the schematic form, and you sum over all of the different propagator structures that you can have. Okay. At 4 point, there's not a lot you can do. You can have a S, T, or a U channel, S, U, or a T channel. And here now I've, the color factors are written in purple, and the kinematic factors are written in pink. And because these are structure constants, they satisfy some Jacobi identity. And identical to this Jacobi identity is a kinematic Jacobi identity, which is also satisfied by nonlinear sigma model amplitudes. And while I've shown you this for A4, this actually happens for all endpoint tree level amplitudes. So, which is why it's called color-kinematic duality. And a very similar structure also follows at loop level, except that this kind of thing happens to the integrand and not the integral. Okay, good. So the objective of the talk will be to see how to define nonlinear sigma models as effective field theory. So how can I add high derivative corrections? What is the guiding principle? And the two guiding principles we'll look at is one is the soft behavior, and the other one is color-kinematic duality. We'll understand how these are related to one another. And in the last part of the talk, I will use the fact that I've constructed this color-kinematic dual NLSM to construct its double copy. I'll tell you exactly what that means. But that will give you amplitudes in this second theory of scalars called Galilean theory. And we'll see what nice properties Galileans inherit. Okay. So any questions about what is the general picture? What we're going to talk about? Cool. Okay. So amplitudes in the NLSM. So here what we're going to do is we're not actually going to talk about the color dressed amplitude, but the color stripped amplitude. So we'll separate out the traces of generators in this way. And what we'll construct is these coefficients over here, or the partial amplitudes. Okay. Now, because traces are cyclic, I can always fix the position of particle 1, and then this is some permutation on the labels 2 through n. Okay, so we'll deal with these partial amplitudes. Now, as I said, these amplitudes over here, they have to actually be cyclic because they multiply in the trace, which means, for example, at 4 point, I have to write down something which could come from a 2 derivative Lagrangian, so it needs to be order p squared. In addition, it needs to be cyclic. There's actually not a lot you can do. There is another structure you can write down, but I'll tell you that I'll show you that actually can't be completed to a soft amplitude. So okay. This is the 4-point amplitude. And you remember that all endpoint amplitudes have this property, right? That the amplitude vanishes when I take one of the momentum soft. So now this is the general principle of what is called the soft bootstrap, which is that I'm going to try and construct the 6-point amplitude simply based on the fact that it is a soft amplitude and that it is a local amplitude. So because it's a local amplitude, I know that it needs to have 4 terms that look like this, right? Which means that when I sit on the pole P1 plus P2 plus P3 whole square equals 0, then I need to factorize into a product of 2 4-point amplitudes that looks like this. Okay? So these S's over here are Mandelstam invariants Pi plus Pj whole square.
I think this is locality plus unitarity, but I think it's fine. Yeah, of course.
Good. So locality, So locality is the fact that you have a pole here.
Yeah, unitarity tells the pole factorizing.
You factorize on the pole. That's right. I will say that there is some ambiguity over here in how I define A4 on either side, because in 4-point kinematics, S13 and S24 are the same, right? But I've chosen S13 over here. And basically, if I changed how I define this, it would just be an overall contact contribution. And because in the next step, I'm just going to add every possible contact contribution, I don't actually care what I'm doing on the pole. Good, so now I have my 3 pole terms. The most general possible contact term I can write down, that is cyclic. And then all I'm asking of this amplitude is that it vanishes in the soft limit. So now here, this equation, for example, is telling me that when P1 goes to 0, the contact term has to equal minus SP5. I repeat this for every single momentum. I do P1 goes soft, P2, P3, P4, P5, P6. And then that fixes the contact term fully. Okay. So basically, the soft limit fixes the 6-point amplitude completely.
I have a question about this contact term. So, before you fix it, don't you have a basis for the contact term first?
Yeah, so this is the most general possible, with some ansatz.
Some contraction, some.
Yeah.
Because, I think maybe because the scalar is easy. But I'm trying to say when you try to generate the higher spin particles, to clarify the contact term is not easy.
It's true, yeah, it's not easy, but the general principle still works.
Yeah, great, that's great, yeah, that's great.
Yeah, so you can just like check for little group scaling and you can check for cyclicity and yeah.
That's true, yeah.
Yeah, but it gets increasingly worse as a calculation to do.
Yeah.
Yeah. Good. But here it's just Mandelstam, so it's not.
That's easy. Okay, for scalar it's fine.
Yeah, I think vector is also not too bad. Fermions are the really annoying ones. Okay, so so good. So this works at 6 point, and I want to point out that actually it works at every endpoint. And let's see whether or not this is surprising. So when I say that something is surprising or non-trivial, what does that mean? It means that I can always write down a Lagrangian which has a certain non-linearly realized scalar symmetry. So let's say it's just shift symmetry. I can build my Lagrangian out of derivative on phi, and necessarily my amplitude is going to have order P soft behavior, and it will have phi delta phi plus C symmetry, shift symmetry. So this is the most trivial way of recognizing or of writing down a Lagrangian with the symmetry. So similarly, if I have some more, so instead of just a constant, I'm allowing something to be a polynomial. This will be a symmetry of a Lagrangian built out of 2 derivatives on phi, and then the amplitude will have OP squared soft behavior. So that's what I'm calling trivial soft behavior. Non-linear sigma model, on the other hand, the Lagrangian looks like this, and so it is non-trivial that it has shift symmetry and soft behavior. Okay, so it is surprising in that sense. Okay. Good. So what have we learned so far? We learned that if you say that your amplitude behaves like this in the soft limit, that means that it has some non-linearly realized symmetry, and that there is some trivial way of recognizing the symmetry, but we will only deal with non-trivial ways or exceptional ways of recognizing such symmetries on shells. Okay. Good. So as I alluded to before, there are some recursion relations you can write down that show you that at endpoint, the procedure that we did at 6 point continues, right? So this is just, what is a recursion relation? It's just a way of constructing a higher point amplitude by gluing together 2 lower point amplitudes. Okay? So in the case of something like a non-symmetric space, you would have an additional term over here instead of just this contribution. Yeah. But in the case that you do have such a contribution, it's very easy to read off things like charge conservation, for example. So if the lower point amplitudes conserve some abelian charge, this has to conserve that abelian charge. But if you had another term sitting over here, because you're a non-symmetric space, then that's harder to read off properties like that for all endpoint amplitudes. But it's still possible to write down such a recursion relation in that case. Okay, so this is all just that the amplitudes vanish. But there's actually more, so the soft gluon theorem, for example, tells us that there's actually more structure than just the order of soft behavior, right? For example, for Yang-Mills, if you take the soft limit, it's actually proportional to the n-1 point amplitude. Now, for nonlinear sigma model, you only have even point amplitudes. Okay? So necessarily you can't have a relation like this because there is no n minus 1 point amplitude, right? So instead, instead what happens is that you find amplitudes in what is called an extended theory. It's basically a different theory which now includes the Paranjape pi and some other scalar states phi. Okay. This is the general structure of the soft theorem. And I call it a soft theorem as opposed to a limit because it's not just the fact that it vanishes at order p, but it's telling you what the coefficient at order p is. And that is an amplitude that belongs to this theory, which is the regular NLSM, and it includes a scalar phi, which has two color indices and a cubic interaction. Okay, so it looks, the 5-point amplitude, for example, that you would get in the soft limit of a 6-point amplitude would look like this. So it has some contributions. Interestingly, this extended theory that sort of lives under NLSM also has color-kinematics duality. So it should tell you that the presence of this extended theory actually is related to color-kinematic duality.
Okay, I want to ask this extended theory. So, is that a proof this one apply to any endpoint on shell amplitude? Is there any proof or just a conjecture?
So I would say it's neither. I mean, so it's not a proof that this applies to any amplitude. In fact, I don't. It doesn't apply to any amplitude.
No, I'm just saying in nonlinear sigma model. Within nonlinear sigma model,
yeah.
Can you prove this extended solved theorem is just a nonlinear sigma model plus phi cubic to any endpoint on shell amplitude?
No.
It's a conjecture.
No. So you can't. I mean, more strongly than you just can't prove it. It's not true. So I can give you. So okay, for NLSM 2 derivative NLSM, this is true.
Okay.
But the minute you look at a 4 derivative, 6 derivative term, it's no longer true.
Oh, sorry. Let's fix on a p square.
Okay, so p
Total
square, this is true to all n.
They already proved it, or just a conjecture? I have this expression. It's just a conjecture by this CHY scattering equation. Maybe it seems that changed. Is there a proof?
I guess that depends on whether you think CHY is proved or it's a conjecture.
CHY is a conjecture, right? We know it's not proved, right?
I mean, it is a conjecture and it isn't, and I'll tell you what I mean by that.
Okay.
So they put forth a formula. That formula respects locality and soft behavior.
Yeah.
Now you have other on-shell reasons to believe that, which I showed you, like the recursion relations, that tell you that if you have an object that is local, factorizes, and has soft behavior, then that is an NLSM amplitude.
Okay.
So which means that the CHY formula gives you the NLSM amplitude. Because it gives you an object that is local, factorizes, and has soft behavior.
You're saying if I say if I say CHY scattering equation is exact, let's say, then this one is the proof. This one also exact.
Yeah.
Kind of. Okay.
Yeah.
What does the 6-point amplitude diagram look like before you take the self-limit for like this 5-point amplitude?
Yeah, it looks roughly like this.
And when you take the self-limit, you can just treat it as the 6th particle is not there?
So let's say you take, so let's say you took particle 6 soft. What you get would have to still be Lorentz invariant, right? So the order P6 term would have to show up as a Mandelstam invariant. So I can just write it as a sum that looks like this, right? With an, basically. This is the general structure, most general possible. One of these I can remove by momentum conservation, right? And so that would be the general structure. What I'm saying here is that something else happens, that actually you don't go all the way to n-1, you go to n-2. And that's what allows you to identify the stuff that it multiplies as an amplitude of a different theory.
Okay.
Yeah. Now, if you want to directly match these diagrams to those, that's not that easy to do. Yeah. Okay. Okay.
It's not easy to write down Lagrangian, right?
For this object?
Yeah, for non-linear sigma model plus phi cubic incentive theory. Every interaction term, every coefficient, I think it might be equal.
I think that's not trivial, mainly because you get these contact interactions.
Yeah.
Yeah, I don't think that's been done.
Okay.
Okay. So another aspect of the soft behavior of nonlinear sigma models is that you have double soft theorems. And because I'm dealing with color-ordered amplitudes, depending on where the two lines that I'm taking soft are with respect to one another, there are different kinds, right? So if I take an adjacent soft limit, for example, you can see over here, if I take 1 and 2 soft, that puts this propagator on shell. So actually, what happens, and you can kind of already see that this is going to give you a factor of p, this is going to give you a factor of p, and this is going to give you a 1 over p, in some broad sense. And so, 1 over p squared, and so what you get is something that is constant, right? So this is a non-vanishing double soft theorem. There's also the next to adjacent soft theorem and the non-adjacent soft theorem. So the next to adjacent says that when I do such a soft limit where I take 1 and 3 soft instead of 1 and 2, I get this factor sitting out in front. And then the non-adjacent is just the same as taking the soft limit twice. Okay. So order p to the 0, order p squared. Now, as I said, our objective is going to be to see how much of the soft structure survives when I start adding high derivative corrections. Good. So how does one do this? I'm going to be fully on shell. So at 4 points, let's say, I need to write down some little group satisfying ansatz for the 4-point amplitude. It needs to be cyclic, right, because it's a partial amplitude, relabeling, just because there's only one kind of particle. And then, of course, we also have to have locality and unitarity. You can check, you can say that, all right, I want to allow the exchange of particles like this. Does that mean that I'm allowed to have any poles in my 4-point amplitude? And because these 3-point amplitudes are fixed, you can just check that, that you can't have any pole terms, even if you include high derivative corrections to any of this. So what you end up with is just that the 4-point amplitude is some cyclic polynomial in S and T. Okay. And sort of trivially, for 4-point kinematics, if you take S and T to 0, this amplitude is going to vanish.
Sorry, I'm really sorry, but I've lost track of what you're doing. You're going to higher orders in S and T?
Yeah.
And so when you're writing this down, is this this is the 4th order, the p to the 4th term in that expansion?
This is the 4-point amplitude.
The full 4-point amplitude?
The full 4-point amplitude. So this is pi to the n, sorry, pi to the 4 d to the n. So as many derivatives as you want, but 4 fields.
Okay, so you're just making some very general comment about the 4-point function to all orders in the derivative.
I'm saying that given this is all that you want from your 4-point amplitude, that it is an amplitude in a quantum field theory, and it vanishes in the soft limit, basically any cyclic polynomial is.
Okay, sorry, I just wanted to make it clear.
Yeah. So, yeah, at 4 point, it's a trivial problem, there are no constraints. At 6 point, we're going to repeat this soft bootstrap style procedure. So you have 4 terms, add cyclic contact terms, and you ask for soft behavior. Okay? So you do this in the same way as before. And what we find is that every single 4-point amplitude can be completed to a soft 6-point amplitude. And from the point of view of chiral perturbation theory, this makes a lot of sense. Because what it's saying is, I can add a term to my Lagrangian in terms of, let's say, the U's, right, that give me some 4-point amplitude. And because it's in terms of the U's, it is necessarily allowed in chiral perturbation theory, and so there must be some completion to a soft 6-point amplitude. Okay? So this is this is something that one would expect from the point of view of chiral perturbation theory, that every single 4-point correction can be completed to a soft 6-point amplitude. Okay. Good. Now, when I say this, I mean that some of the 6-point contact terms are fixed in terms of 4-point coupler extents. Right? So that's what happened when we found the S135 contact term. It was fixed in terms of 4-point coupling constant. Now this is not true when I go to higher orders, because I'm allowed to, I'm now allowed to add contact terms that vanish all on their own. They don't have to interact with the pole terms in order to vanish. So basically what that's telling me is that I have a situation like this, where while at orders P2 and P4, I don't have any contact terms, right? Which is not to say that I don't have any contact terms, but that they are fixed in terms of the 4-point information. But from order P6 onward, we do have contact terms that on their own satisfy what needs to be satisfied for them to be a part of color perturbation. Okay, so you have independent contact terms starting 6 derivatives on 6 fields. This makes a lot of sense, because this is the triviality, right? Because when I have 6 derivatives in 6 fields, I can trivially construct something that vanishes and has shift symmetry.
Sorry, so in the P to the 4th, the 0 and for the contact, I mean, does that, you saying that if I wrote the nonlinear sigma model Lagrangian, okay, a la CCWZ or Weinberg or whatever, I could actually get rid of all the P to the 4th counter terms by some field redefinitions, etc., integration by parts? I thought there were non-trivial P to the 4th. Oh, but it probably doesn't contribute to the 4-point amplitude, right?
Right.
Sorry, yeah.
So here, what this is saying is that, sorry, this is the 6-point amplitude.
Sorry, the 6-point amplitude.
But it's saying that
yeah, it
you
doesn't
get,
contribute, yeah.
so you get two operators, but the coefficient in front of those operators is related to the square of 4-point coefficients, right? In other words, you can write down something in terms of the U's that contributes at 4-point and it contributes at 6-point, 8-point, etc.
Right.
But you can't write down something that starts to contribute at 6-point.
Yeah, okay.
Yeah.
Yeah. So if I wanted to count the number of terms in the Lagrangian, I would have to look at this for all the amplitudes and then, okay, I understand.
Yeah. Yeah. Good. So what happens to the soft structure? So the adjacent double soft theorem, you remember, is the non-vanishing double soft theorem, and that is actually guaranteed by the algebra that the broken current satisfied. And so naturally that is not affected by adding high derivative connections. The next two adjacent double soft was, it basically depends on what your 4-point amplitude is. So naturally when you mess with what the 4-point amplitude is, that next to adjacent double soft theorem is going to change. Okay. Finally, this is related to your question, that basically, is there a higher derivative extended theory that sits under all of these higher derivative corrections, right? And the answer is sometimes, okay? And it makes sense that the answer is sometimes, because this theory over here satisfied color-kinematics duality. So it's kind of strange if you expect that amplitudes that don't necessarily satisfy color-kinematics duality give you color-kinematics dual amplitudes in the soft limit. Okay? So we'll see actually that, we will first talk about color-kinematics duality, and then after that we will see what the relation is between color-kinematics duality and soft limit. Okay. So let's now understand what color-kinematics duality is, why you might want it, etc. So the real reason people started talking about BCJ duality or color-kinematic duality is because of the double coupling. Okay, so this is a structure in the space of theories where you can write amplitudes in a theory C as products of as sums of products of amplitudes in theories A and B. Okay. And the classic example was Yang-Mills, when squared gives a dilettante gravity. Okay. So at 3 point, this is very simple. I literally take the 3 gluon amplitudes, square it, and that gives me the 3 graviton amplitude in perturbative gravity.
So why is the dilation plus 2 form? Dilettante, sorry, dilettante.
You're saying why do I get this
Yeah,
particular? It basically is related to the fact that Yang-Mills has 2 helicities, right?
Yeah.
So if...
But gravity also has 2 helicities, right?
That's right. But it doesn't have 4 helicities. So, so if you take like a double copy, you're going to get a plus plus, a plus minus, minus plus, and minus minus.
You have 4 helicity states.
You have 4 helicity states. So you're going to have to, so you get gravity, which is 2 of them, and then you get a symmetric combination and an antisymmetric combination. And that gives you the dilettante and axiom in 4 dimensions.
Okay, so, but the amplitude involve the gravity and the dilettante and 2 form, they are related, right? The coefficients, they are related.
Yeah, that's right. They are related. It's a particular theory of dilettante gravity.
Oh, okay.
Yeah, I will say though that if you have all external gravitons, these will never appear. So you can just, at tree level you don't have to think about the dilettante in 2 form at all.
Oh, okay. You mean at the, beyond the tree level, at the loop level, you have dilettante.
Yeah, at loop level you have to include some projectors and things to make sure that you only have gravitons propagating in the loop.
Oh, okay, okay.
Which is also why most of the time calculations are done at n equals 8 supergravity, because there the dilettante just is the scalar in the n equals 8 supermultiplier. Okay, so this, as I said, the amplitude of the double copy of A and B can be written as some sum over products of amplitudes in theory A and theory B. Right? And the example is that 4 point in gravity, this 1, 2, 3, 4 amplitude can be written as a square of Yang-Mills with some factor sitting out in front, which is what I call S alpha beta over here. Now S alpha beta was nicely, a very nice form for S alpha beta was given by Kawai, Lowell, and Tai. And I will just say that alpha and beta over here are simply the color orderings that we already introduced before. Okay? So what you're doing in the double copy is you're nullifying color. Now, Cachazo here in Yuan, CHY, extended such double copies to now include the nonlinear sigma model. So you can double copy the NLSM with itself to get this theory of scalars. It's a high derivative theory of scalars called special Galilean theory. Or you can double copy the nonlinear sigma model with Yang-Mills to give you Born-Enfeld theory of photons. Okay? And it's the same, I want to emphasize, it's the same formula as you saw in the previous slide for gravity. It's just the Born-Enfeld amplitude with the same kinematic factor, Yang-Mills times chi pt. Okay. Good. So there are more than just these examples of the double copy. It's been extended to various states. But we'll only deal with massless states. We'll actually only deal with massless scalars. And in that case, you find that the fact that you get a single scalar theory out means that the amplitude you get out must be permutation symmetric. But for this formula to respect permutation symmetry, the NLSM amplitudes have to satisfy this relation over here, which is called the BCJ relation. Now this is just another way of writing color-kinematics duality. And these BCJ relations are satisfied by nonlinear sigma models at 2 derivative order. Okay. So at leading order, all of these descriptions are the same. Soft behavior, shift symmetry, color-kinematics duality, everything gives you the same amplitudes. Good. And I emphasize that it's the same as color-kinematics duality. It's just a different way of writing color-kinematics duality. Okay. So now we can use this as the principle to construct our high derivative corrections. Right? In exactly the same way, you want your amplitudes to be cyclic. you want them to satisfy the BCJ relations. There's this additional technical point that they also satisfy the Christ-Quick relation, which is just to say that the only color factors that appear in your Feynman rules are just structure constants. If that's true, then your amplitudes will satisfy Christ-Quick relations. Okay. So this is the same as before, so let's look at the final answer. So when you do this procedure at 4 point, you find that the NLSM amplitude has to take this form. So I remind you that this T over here was the leading order order p squared or 2 derivative nonlinear sigma model amplitude, which is now allowed to be multiplied by a symmetric polynomial. And such an amplitude will always satisfy the BCJ relations at 4 point. This is necessarily a smaller subset than just every cyclic polynomial, which is what we found by just demanding soft behavior. Okay. So let me just stop to see if there's any questions about what the logic is here.
So you are imposing the double copy to try and get can actually construct the higher point amplitudes, right?
Yeah. So you're saying that this is a symmetry that I want my theory to have. So what kinds of high derivative corrections am I allowed to add to my Lagrangian that satisfy this symmetry? Yeah. Good. So now we do this at 6 point in exactly the same way. You construct pole terms, add contact terms, apply BCJ. Okay. So this is a table that shows various numbers. So these are the number of these are the number of derivatives. These are the number of terms at 4 point. Naturally, at 4 point, all of them are contact contributions. There are no poles, and this is NLSM. At 6 point, I can repeat the analysis, and now I find that the number of BCJ terms. So all of the BCJ terms, first of all, are order p in the soft limit. So BCJ is a subset of soft, right? So every soft term is not a BCJ term, but every BCJ term is a soft term. Okay, good. So that kind of leads you to question, is there anything else that selects out these BCJ terms? Is there any other reason why they're special, or is it just that they have color-kinematics duality? It turns out that actually BCJ is related to the full soft structure of NLSM. So, as I said before, the adjacent double soft theorem, it's true regardless of what kinds of high derivative corrections I add. But the fact that you have an extended theory is connected to BCJ in that if all I impose is that the extended theory exists, then I find that I have to satisfy the full BCJ relation. Okay? So while not every soft term is BCJ compatible, every soft term that has this extended theory sitting under it is BCJ compatible.
Okay. So I'm just not quite sure what the lesson is. I mean, you're saying that the general nonlinear sigma model does not have this structure, right? But I guess I don't know enough what this Kleist, I don't even know how to pronounce it, Kleist-Koof KK property is. I mean, what can you say something of what is the significance of that, or how can I? Because as somebody who doesn't really know what that is, what's the lesson here, or what's the? Can you just say a little more about that?
Yeah. So we'll talk about all of the lessons, but at this slide, really all I wanted to say was, if you just demand chiral symmetry or soft symmetry or whatever, soft behavior, then you're necessarily going to get terms that you're allowed to add in your EFT Lagrangian that are not BCJ compatible. But if I require something a bit more than that, so ignore KK for a second. If I if I require that in the soft limit I get amplitudes of some extended theory, then that actually is the same as color kinematics.
Okay.
Okay, so which is just to say maybe, so soft behavior and BCJ are not at the same footing, but maybe soft structure and BCJ are at the same footing. Okay, and the Kleist-Guif relations are just, it's just a statement about what trace structures you have when you construct amplitudes. So when you write down the partial amplitude expansion with the trace over generators, it's basically saying that you can Fiat-Pauli your way all the way down to just FABCs. That's all. That's the statement of the Kleist-Guif relations.
So maybe kind of a more crazy question. I mean, there's kind of a weird tradition in strong interaction physics where people come up with these principles that are not obviously physical, and they place constraints on couplings of hadrons, you know. So you could just ask, well, are these, is there any sense in the data for which that these things that are not double copy are somehow small?
Good.
Phenomenologically? Is there
is
any hint
some
of that?
hint at this, but I don't think it's well, I don't think everyone would agree that this is true.
Yeah, I think the P to the fourth terms are not that well constrained.
They're not that well constrained.
Yeah.
Some people say that they are small. It's unclear also what small means exactly. If
Yeah.
they're 1 over n suppressed, are they 1 over m suppressed? Yeah, so I think it's not fully understood whether that, what the OP4 terms look like in reality, and so it's not clear whether this is actually a symmetry of nature.
Since you mentioned large n, I mean, in the large n limit, do you get the double copy structure in the large n limit?
Mm-hmm.
You do?
I mean, yes, you
You
do.
do?
Yes,
Okay.
you do get the.
Okay.
In fact, yeah, you do. I mean, for Young-Mills, you get it only in the
Well,
large n limit.
For this theory, here
this
you have an
theory,
SUN cross SUN. Is there any simplification at large n there?
No, not really. I mean, we're already, well, we kind of already only allowed single trace.
Okay.
So,
All right. So you're already sort of.
so you're sort of already large
Okay.
n in that sense. Yeah. Okay, so this is sort of the summary of just when you do this program in 4-point and 6-point, you get a bunch of things. I'm not really expecting you to get much out of these numbers, other than the numbers exist. So if you want to play with them for any other reason, you can. Okay, so let me point out 3 interesting features of this analysis that I find interesting. So the first is 4-point selection. Yeah.
Yeah,
sorry.
so in your previous page, I see bootstrap and I see this term a lot, but I don't really understand what it means. Can you explain a little bit?
So there's a very formal sense in which people use the term bootstrap in the conformal field theory. It's not what I'm saying here. When I say bootstrap here, what I mean is with minimal amount of data, how much can I say about higher point amplitudes? So here, for example, when I say soft bootstrap, I mean all I'm asking from the amplitude is that it's soft. What am I allowed to have? BCJ bootstrap, all I'm asking from the amplitude is that it's BCJ compatible. What am I allowed to have?
Okay.
Yeah, this is sort of a loose way of, it's I guess the English term bootstrap, not really the physics term bootstrap, if you will. Yeah.
So can I see from this table, can I see how many independent operators at each level is actually refer to the number in the contact term?
Yeah. So that's the, exactly.
But have you checked with the previous literature? I believe that do they have some result that for them P to the 6?
Yeah, so I mean, these numbers will necessarily be less than the Lagrangian numbers. Because some of the operators that people write down in the Lagrangian will not contribute at 4-point or will not contribute at 6-point. They'll contribute at 8-point, for example. So,
I think the Hilbert series methods give you these, you can count all
Yeah, you
the
can-
complete
Yeah.
numbers of contact terms
Yeah.
using Hilbert series.
Yeah, have you double check with the literature
I think this
the
matches.
number matches?
I think the 4-point matches.
The 4-point matches, okay.
I don't know about the 6-point.
Okay.
Yeah, because I don't think anyone has done, yeah, you have to go pretty far.
Mm.
Yeah. Okay. So like to point out is that the first time you get two different 4-point amplitudes is at 14 derivative order. Okay? Which means that, and that 14 derivative object contributes over here in the pole terms. Right? Now, unlike in the case of the soft bootstrap, when you do the BCJ procedure, not every 4-point amplitude can be completed to a solution. Okay? So here, for example, we're allowed to have two terms, but we get only one solution. Here, we're allowed to have this, this kind of pole term, but you find no solution. Okay? So there are two things that happen here. One, if you allow this term to mix with this term, or this term to mix with that term, then you get a solution. And also, if you have two allowed terms of the same order, there's some selection procedure that fixes the lower point in terms of the higher point. Okay? So
when you say mix, you're meaning that you're breaking this factorization of that you have in the double copy or BCJ? Is that
no,
what you
actually,
mean by mix?
I just mean that if I was to add, so you would assume that, say I was allowed to add some 6 derivative operator to my theory, it would have nothing to do with the 8 derivative operator.
Right.
Like these two coefficients would be completely independent. Unless there was some UV reason, I mean, so if you did the full top-down calculation, they might be related.
Right.
But from just the IR point of view, there's no reason for a 6 and 8 derivative operator, their Wilson coefficients, to have anything to do with one another. But BCJ relations will tell you that this and this will have to be related in some way.
I see.
And similarly, 6 and 10 and 6 and 14, etc. So there's some cross-derivative mixing that BCJ requires you to satisfy.
I understand.
Yeah.
Okay.
Even though it's just some IR relation, it's just some relation that the amplitudes have to satisfy in the low energy domain. Yeah. And the second is what doesn't happen with just chiral perturbation theory, that the 6-point and 4-point coefficients are also related. Right? So, or rather, the 6-point calculation puts constraints on the 4-point coefficients. So it's not like everything at 4-point continues to work at 6-point. And in particular, the selection that we see appears in what is called Z-theory. Okay? So Z-theory is not a theory, despite its name. It's just a set of amplitudes. Okay, maybe you can't even call them amplitudes. It's just a set of kinematic objects that show up when you want to write the open string as some QFT part and some stringy part. So the stringy part is some disk integral, and the QFT part is just superdynamics. And I'm calling that disk integral Z-theory. And the reason that I would like to think of it as a theory is because when you take alpha prime to 0, it just gives you the NLSM plus some high derivative corrections. And those high derivative corrections satisfy the BCJ relation. So everything that we have been doing is just this amplitude will be a subset of the more general analysis that we've been doing with BCJ. Okay? So, yeah, at 4-point, not all possible BCJ corrections are generated, and so you get some selection, and one of the possible selections is the one that shows up in Z-theory.
So are you saying this is an explanation of the previous result, because it's known that this open string has this double copy, and so it descends in this way to this particular version of the nonlinear signal model?
Right.
Okay.
And I'm saying that the fact that this happens might be indicative of BCJ relations telling you something about good UV behavior. The last point I'd like to make is just that even though I've presented you with some finite numbers, I can multiply all of these by some symmetric polynomial and I'll still satisfy the BCJ relations. So I've actually presented you with an infinite set, okay? Because I can always multiply an with some symmetric polynomial, and that gives me another contact term that works. There are infinite symmetric polynomials, so there are actually infinite BCJ contact terms that exist.
Right, I'll just come back to the question about the UV limit. I mean, you could certainly at tree level, you could imagine various just scalar completions of this theory. You know, just kind of multi-Higgs model type things, right? And at tree level, at least, it's very straightforward to just generate the low energy effective Lagrangian, right? And so you could just ask, you know, do these relations, these double copy type relations, in any way come out from those? Those have decent high energy behavior. They're not as, you know, they're not as soft as string theory, but they're I don't know. Would you expect anything good to happen there? Guessing not, but I don't know. Or would you expect these double copy relations to come from something like that, just a tree level scalar theory?
I mean, it's okay. So when let me go back a bit. So when I say that Z theory is contained in such relations, it's obviously still a low energy thing. So I mean, it's not like I'm not going to get zeta values or something from this. Right? I'm not going to fix those coefficients. They're still Wilson coefficients. There's just some like relations between them that must be satisfied. So
right.
It's possible that a theory like the one that you just said with some Higgs completion still lies in this.
Exactly. That's what I'm asking you. Is anything known about that? Or?
No, actually, not that I know of. I think one thing that is sort of left to be done is this, what people are calling positivity constraints, to see what high derivative corrections, which coefficients satisfy these positivity constraints that say that there is some good UV behavior. And that will formalize this sort of more indicative calculation, which is like, maybe there is some connection, versus the positivity calculation, which will concretize this and say.
Sure, but these are actual equalities, right? I mean, you have to satisfy certain equalities to get this structure. So.
Yeah, absolutely. There's an equation I can give you that has to be satisfied by the coefficients. Yeah. Yeah. So I guess in principle you could take a model like the one you suggested, take the low energy limit, look at what the coefficients are, and see if these equations are satisfied.
Yeah, I don't know if there's much known about that at these high derivative orders. That there might be some structure there. I don't know.
It also might be possible to just calculate the low energy amplitude.
That's what I mean. I mean, you start with some theory with some heavy scalars, you know, with arbitrary couplings, and then the low energy theory is this, because you have the symmetry breaking pattern, and then you compute the low energy parameters as a function of the high energy ones. And like I said, at tree level, that's a very, you can just turn a crank, it's very, and you can just ask whether these relationships somehow emerge.
Yeah, I think that's an interesting question.
Right, I don't know.
Yeah. I mean, yeah, I think that's an interesting question. As I said, I think also the more general positivity calculation would it would just be more general.
They would certainly satisfy those relations.
Yeah. Okay. In terms of time, how
How much time
more
do you
time?
need?
You're at 37 out of 46?
No, I mean that's the sort of
Why don't you go for...
aspirational number. It's okay. I mean,
Officially, you have 0 minute, but but you can continue.
Go for another 10 minutes or something, and then wrap up, and then we can continue discussing. People, and people who are, you know, not as into it can leave, and we can keep discussing.
Yeah.
Okay.
Sounds good. I don't want to hold people hostage. So let me sort of, in a lightning fast way, talk about the last part, which was what is the double copy of such theories. Okay. So the double copy, this is the actual KLT formula. Okay. This is the explicit formula. Earlier I called this S alpha beta. Now I've given you the actual form. It doesn't matter. It's just nice that it exists and it's concise. And I'll remind you that if I plugged in nonlinear sigma model amplitudes here and here, I'll get out an amplitude in some single scalar high derivative theory called the Galois theory. Okay, good. So can we use the fact that now we know a lot about the NLSM soft structure to say something about what is happening to the special Galileon's soft structure. So the first is just the soft behavior. So you can just take P1 to 0 in the double copy relation, and you find that this equation has to be satisfied, where sigma tells you how soft the amplitude is. Okay? So you remember that for NLSM, the amplitude goes as order P, so sigma is 1. So this gives you 1 plus 1 plus 1, which is 3. And you find that double copy amplitudes that are constructed from the non-linear sigma model all have order P cubed soft limits. Okay? Yeah. Now you can go in the opposite direction and say that, all right, one way to construct Galilean theory with high derivative corrections is to do the double copy. But the other is just to say that I know that my amplitudes have order P cubed, what do I get? Right? And as we saw in the case of NLSM, doing a soft bootstrap isn't the same as doing a double copy bootstrap. And we find that something very similar happens with Galilean theory. So this is the table for Galilean theory, and you get some corrections, and they are a subset of all possible order P cubed corrections. Okay. Good. Now this is something that's not quite complete yet, which is the idea that we saw that the existence of this extended theory for NLSM places the same constraints on the high derivative corrections as the BCJ relations. So now we can ask the question, does the existence of an extended theory for Galileans tell you which corrections come from the double copy? This is still an open question where we're looking at this now.
So the special Galilean is not Galilean. It's the
special Galilean.
It's special. Can you explain a little bit what you mean by special Galilean?
Yeah, so the Galilean theory is usually one that people say has order P square soft limits.
Yeah.
So it has some non-linearly realized symmetry that looks like phi going to phi plus
C mu, X mu.
some quadratic, yeah, exactly. Some linear.
Linear, yeah.
Yeah.
Then you're saying special Galilean plus quadratic.
Good, yeah. So it has some acceleration term that looks like
This was discovered by who? Special Galilean? By Yara? Or?
No, well, people have studied it in the context of modified gravity for a while. Before...
Not by Yataze and the collaborator.
Yeah, not by them.
But I forgot who.
But I think it was seen before in the context of some massive gravity decoupling limit.
Oh, okay.
I think. Or maybe Aristotle discovered it.
Okay, sorry.
I don't want to, yeah,
okay,
I don't want to say because I can't remember exactly what
Okay, go on.
Yeah.
Sorry.
But it was definitely, at the very least, rediscovered by them because of the nice properties and the fact that you can construct the amplitudes with the soft recursion directions.
Yeah, okay.
Okay. So additionally, you can also get the double soft theorems from the double copy because the Galilean amplitudes are related to the NLSM amplitudes. Okay. We will skip to this last sort of point that I wanted to make, which is that we sort of have this nice completion of NLSM amplitudes that is BCJ compatible, which is Z theory. It's also known that Galileans cannot be really completed, at least in a normal way that one tries to do it, which is that you couple it to some massive states, possibly with higher spins, and then in the low energy, and you want it to be unitary to very high energies, and then you say that in the low energy limit I get some EFT, right? So in that sense, this paper, many papers actually show that you can't actually complete Galilean. Which then begs the question, what actually do you get when you double copy Z theory with itself, right? Do you get some, so I mean, normally you would say, okay, this is a disk integral, that is a disk integral, KLT should tell me that I get some sphere integral, for example. And it's not actually known what you get over here, and then whether taking the low energy limit of that gives you a special Galilean theory, which would give you some indication of a possible UV completion or some way in which you get such a modified scalar theory. Yeah.
Okay.
did you have a question?
No, go on. Sorry. I just,
So Z theory is not, as you said, not a theory. It's not, doesn't have the properties of scattering amplitudes. But is the idea that Z theory cross Z theory somehow makes sense as a set of scattering amplitudes? Or maybe I'm not sure what you're saying.
So maybe I was too strong in what I said. So Z theory is not a theory in the sense no one has written down a Lagrangian.
Yeah.
Z theory is not a theory in the sense that if I wrote down the Z theory amplitudes, it would look like the Veneziano amplitude.
Okay.
Which, can you think of that as a QFD amplitude? It's a little unclear because it has an infinite number of poles.
Okay.
Yeah.
So
So
at least as a
stringy
tree-level
in that
amplitude,
sense.
it's a physical amplitude. So I was under the impression from what you said before that Z theory, just as a set of amplitudes, didn't even make sense as a tree-level amplitude. But maybe
Yeah, so I
maybe
mean, I guess
didn't.
as I said, depends on whether you're thinking of the Veneziano amplitude as a tree-level field theory amplitude.
Okay. It's in
Yeah.
the same sense.
It's in
as
the same
that.
sense.
Okay.
It's some bunch of gamma functions
Okay.
at 4 point, for example.
But I mean, Veneziano, I mean, it was a big deal precisely because it is a very plausible looking tree level, at least amplitude, right?
Yeah,
so,
absolutely.
So Z theory has all those kinds of
It does have
properties.
a lot of very, very nice properties,
okay.
like the Veneziano amplitude.
Right.
But there you know that it comes from some open string scattering.
Eventually,
here-
yes,
You don't know what this is scattered in.
I see, right.
There is no like underlying string theory. There is no theory anyone's written down, basically.
Okay.
Yeah. Yeah, which is why I guess in some sense you could say question mark times question mark equals question
you got the
mark.
question mark as
Yeah.
well.
But-
Hard to disagree with.
Okay. So, good. So there's more to be said about all of these things, especially after doing the double copy. But even before, I think the main question I would like to answer is if you keep doing this to higher point, do you just get closer and closer to the Z theory amplitude? So, in other words, and more importantly, if you did this for Yang-Mills and gravity, do you just get closer and closer to the open and closed string amplitudes? Okay? Is that sort of the only thing that you're allowed to have? And then, in which case, can you actually use BCJ as a test of UV health? Okay. At the technical level, these two questions also exist, which is why does the BCJ relation give you a vanishing soft limit? It's kind of unclear why this happens, but it does. I mean, so it's a strict subset of the soft connections. And finally, the fact that you have this mixing in derivatives and mixing in endpoints suggests that you can possibly write down a BCJ Lagrangian, right? But what that would look like would now be interesting, because it wouldn't be every possible combination of U's with derivatives or whatever. It wouldn't just be chiral perturbation theory, it would be some special version of chiral perturbation theory. Good. So maybe I'll skip the summary slide and I will, I'll see if people have questions. Thanks.
When I introduce a double copy S coefficient, how do you know that's purely kinematical?
Good. So this one over here, right?
Sure, or from the very original formula when you introduce a double copy, same thing, yeah.
Yeah.
Integrals are ut over S, right? But
Yeah.
why is it purely?
So it's purely kinematic. You can kind of see that because if you look at, so what could it have if it wasn't kinematic, given that it has to give rise to something that's Lorentz invariant, right? It could only have something that's like a polarization vector. That's the worst it can do in some sense. And the reason it doesn't do that is because if you look at how the little group acts on all of these objects, so M, S, A, and A, you'll find that the fact that we're multiplying two A's together will actually take care of the little group weights of the particles in M, which means that S is not allowed to have any little group weight, which means it has to look like scalars, which means it has to be just Mandel-Stan invariants. So the fact that S is kinematical just comes from the fact that stuff needs to be Lorentz invariant and little group covariant. Yeah.
Another question I have is, you mentioned some coefficients are not constrained because they don't mix with the pulse, and then you go to higher order in the momentum, and we see that the difference between the number of terms that you actually have, it goes like 700 or something, the other is like 690. It seems like only 16, 10, like on the order of 10 terms that's not constrained. I wonder if those coming from the original theory has some underlying structure that make only say 20 terms not constrained because they don't mix with the pulse while others do. Does that make sense? I'm not saying there is a underlying structure. It's possible there may be some underlying reason why.
I mean, I think though it's hard, right? Because
if it goes like a P6, or maybe you can write down everything and see like which ones exactly are not constrained. But say we go to P18, okay, we have a difference of 37.
Yeah.
Now which 37 coefficients are we talking about? And in the original theory, can we track down, calculation with?
Yeah, so actually, because of the way that we do this, right, which is that we have some, we have some pole terms and then we have contact terms.
Right.
I have an ansatz for the 4-point amplitudes, and I have an ansatz for the contact terms. Now, at the end of this, it comes out to some like calculation of number of linearly independent coefficients.
Right.
And that is, let's say, 18, 19, right? Then I can say, all right, how many of these are products of coefficients, and how many of these are coefficients? Because necessarily all the pole terms will come from products of coefficients, and those will come from coefficients. And that will tell me that there are 1772 of them that are not products, so they're contact contributions, whereas the rest come from poles. So now I already know that this difference between these, which is like what, some 18. Some number that is all of the pole terms, and I know exactly how to construct the pole terms because I know exactly what the 4-point amplitudes are. Does that make sense? Okay. So
I guess my question is what's the relationship of among those pole terms?
So for the soft amplitudes, there is no relationship.
So what?
For the BCJ amplitudes, there is a relationship between them, and that's the main difference between these two analyses. That for soft amplitudes, you don't get any relations between the pole terms, whereas for BCJ amplitudes, you get things like this, where this and this have to have some relationship in order for a solution to exist. Right? Yeah. So this pole term needs to be related to this pole term in order for a solution to exist. But that doesn't happen if you just need soft behavior.
So in the Lagrangian language, I would say that I'm working to some order, let's say, I guess, 14th order or whatever, p to the 14th, and up to this point, it looks like I've got all these independent terms. But then if I want this double copy structure to keep working at p to the 16, I find that I would have had to chosen some relations that involve my existing coefficients already. So I'm finding constraints on the p to the 14th Lagrangian from higher consistency with this BCJ thing at higher orders. Is that correct? Did I understand that right?
That's right. Yeah. So, which is again, which is what I meant when I said, how do you write down a BCJ Lagrangian? That actually works to some finite derivative order. Which works if you just have order p squared. And that 2-derivative Lagrangian works.
Right.
That works all on its own. But once I start adding other things, they don't work.
Right.
So it's not like if I wrote down everything up to P14, like you said, it would be color-kinematic compatible.
So is it known if I said let's say I was interested in some order, fixed order p to the fourth or whatever, some fixed order like that where there's more than one coefficient, okay? And now I want to require, this double copy structure to all orders in P. Do I know that how many independent terms there are? Is it impossible that there's one? So in some sense, maybe there's one unique theory that would work to all orders is kind of what I'm saying? Is that sort of question addressable, or is that just way beyond what you could actually hope to do?
I mean, at the level of doing the actual analysis that you're suggesting, I think it's impossible. At the level of whether there exists just one, there exists more than one for the nice reason that, so Z-theory satisfies this, but Z-theory has these coefficients which are zeta values.
So you
Zeta
already
values
know
are
it's
independent. Yeah.
You
so
know it's not unique.
I know it's not unique.
Okay.
Yeah. So you could just replace the
So
zeta
there are at
values
least
by
that
generating
many parameters, right?
and they're infinite zeta values.
Okay.
So,
Oh, okay.
yeah. Yeah. So you already know that it's not unique, which is why the setup that you suggested might still work, or might still be VC2 compatible.
Well, what are you doing working on a theory that's not unique?
I mean, that's every DFT person ever, I feel like. Yeah.
Any other questions? Anyway, let's thank Shruti. Sorry, I should have done this a while ago. People want to stay, can keep trying Shruti's patience.